A throttle opens. The locomotive lunges forward. The train behind it doesn't move. Cast steel couplers, built to hold 100 loaded cars together, snap under a force they were never designed to survive. Cars sit dead on the track while the front end pulls free, dragging nothing but broken iron. No collision. No derailment. Just one machine so powerful it ripped its own train apart from the coupler back. This wasn't a freak accident. It was the inevitable result of building the single most powerful locomotive in American railroading history and discovering the hard way that the engine was never the weakest link. This machine was Union Pacific's third-generation gas turbine electric locomotive, known to railroad crews and historians simply as the Big Blow. At a time when a standard diesel-electric locomotive of the era produced roughly 2,500 horsepower, the Big Blow was rated at a continuous, certified 8,500 horsepower. The true marvel, however, was how Union Pacific packaged this colossal output. In the post-war freight boom, hauling thousands of tons of cargo over the steep mountain passes of Wyoming and Utah required railroads to string together a long line of multiple diesel units. This process required massive coordination, extensive maintenance, and several crews. The Big Blow bypassed that entire setup. It consolidated the pulling power of a triple diesel lash-up into one single locomotive unit. This design delivered a continuous, tractive effort of over 212,000 pounds. It was the most powerful single-unit locomotive ever to enter regular revenue service in North America, and indeed, the world. Stationed at the head of a freight run, this single machine replaced 4 or 5 conventional locomotives, concentrating an unprecedented amount of force onto a single drawbar. Union Pacific had built a mechanical titan, a single-unit powerhouse designed to conquer mountain grades on an unheard-of scale. But in doing so, they focused entirely on the machine itself, setting up a direct conflict with the limits of the infrastructure behind it. At the end of World War II, Union Pacific Railroad faced a staggering surge in demand. Annual freight tonnage shot up 50% in just one decade, climbing from 140 million tons in 1945 to 210 million tons by 1955. To keep pace with America's roaring post-war economy, the company had to move heavier, longer trains over some of the most unforgiving mountain terrain in North America. The immediate bottleneck was the rugged geography of the American West. Routes like the Wasatch and Moffett corridors presented steep grades of up to 2.2% combined with tight, sweeping curves. Dragging thousands of tons of cargo over these mountain passes required immense, sustained pulling force. Under standard operations, the only way to conquer these climbs was to string together multiple diesel locomotives, often adding extra helper engines to the middle or rear of the train. But this multi-engine approach came with severe operational and financial penalties. Managing a long consist of separate locomotives meant coordinating multiple crews, synchronizing complex throttle inputs, and maintaining dozens of individual diesel engines. It turned train dispatching and fleet maintenance into an ongoing logistical headache. Union Pacific's leadership wanted a simple, more practical solution. Instead of managing a complex lash-up of 4 or 5 separate diesel units, they sought a single, massive machine capable of doing all the work alone. This quest was not driven by corporate vanity, but by cold operational logic. The giant locomotive was conceived as a highly functional tool to slash crew costs, simplify dispatching, and master the mountains through sheer, concentrated power. To achieve this scale of power, engineers abandoned standard piston-driven diesel engines. The heart of this new machine was a massive gas turbine, a power plant derived from the jet engines then transforming military aviation. Instead of pistons moving up and down to turn a crankshaft, this locomotive used a continuous blast of hot gas to spin a turbine shaft at thousands of revolutions per minute. This spinning shaft was directly coupled to giant electrical generators, which produced the massive currents needed to feed the traction motors down on the axles. The choice of turbine technology was tied to a specific economic strategy. Gas turbines were notoriously fuel-thirsty, but they could run on a fuel that conventional diesels could not use: bunker C residual fuel oil. This heavy, unrefined byproduct of petroleum distillation was practically a refinery waste product, selling for a fraction of the cost of refined diesel fuel. It was so cheap that its low price promised to offset the turbine's high rate of consumption. But this tar-like oil, with a heavy API gravity of 10 to 12, brought extreme physical challenges. At room temperature, bunker C is highly viscous, resembling cold molasses. It cannot flow through standard pipes, let alone atomize in a combustion chamber. To overcome this, the locomotive carried a complex onboard heating system. Heavy-duty 5-kilowatt electric heating coils and steam lines ran through a 10-gallon preheat tank in the nose of the unit, warming the fuel to nearly 200 degrees Fahrenheit. On cold days, crews had to wait through a 15-minute preheating cycle before starting the turbine. Only when heated to this near-boiling state did the thick residue thin out enough to behave like a liquid, transforming from a sluggish, semi-solid sludge into the high-energy fuel that propelled this giant. Once that preheated bunker C fuel finally ignited inside the combustion chamber, the locomotive ceased to be just a machine and became an auditory phenomenon. In March 1955, a Union Pacific employee newsletter coined a name that stuck instantly: the Big Blow. It was a nickname earned through sheer, deafening volume. The gas turbine did not chug or thrum like a traditional diesel. Instead, it roared with the continuous window-rattling shriek of a military jet taking off. On calm nights, residents across the valley in Ogden, Utah, could hear the locomotives howling exhaust from their homes, miles before the head of the train actually appeared on the horizon. The extreme noise created immediate operational problems. A 1956 Union Pacific safety study recorded sound pressure levels of 95 decibels at a distance of 50 feet from the exhaust stick. This output easily exceeded the 85 decibel threshold for occupational hearing protection, posing a constant hazard to yard workers and train crews alike. By 1957, municipal noise ordinances in Salt Lake City classified the turbine locomotives as a potential public nuisance. The civic backlash forced Union Pacific to adjust its operations, restricting the locomotives to off-peak hours or routing them entirely away from populated urban corridors into the open, remote stretches of desert and mountain pass. The very physical presence that made the Big Blow a marvel of concentrated energy had turned it into an outcast in the towns it was built to connect. Every ounce of the Big Blow's 8,500 horsepower had to pass through a single, physical point before it could move a single ton of freight. This bottleneck was not located inside the massive turbine, the giant electrical generators, or the heavy traction motors geared to the axles. It was the coupler, the knuckle of cast steel, that connected the locomotive's rear drawbar to the very first car of the train. And here lay the central engineering paradox of the Big Blow. The locomotive was not limited by a lack of engine output, but by the physical hardware required to transmit that output through the rest of the train. In the mid-20th century, North American freight cars relied on standard Janney, or E-type couplers. These couplers were rugged, mass-produced components, but they possessed a very finite mechanical limit. A standard E-type knuckle of this era was designed to withstand a static load of roughly 120,000 pounds of tension, with an impact limit capping out around 150,000 pounds. Beyond these thresholds, the cast steel would undergo plastic deformation, warp, and ultimately tear apart. When the Big Blow's turbine spun at full operating speed and the engineer advanced the throttle, the electrical generators delivered a massive surge of current to the traction motors. If this enormous energy was applied too rapidly, the resulting drawbar pull spiked instantly. At the head of the train, the coupler on the lead cargo car became the narrowest throat in the entire force path. When these starting forces surpassed the structural limits of the steel, the coupler did not simply slip, it fractured catastrophically. In rail yards and mountain passes across Utah and Wyoming, these knuckles sheared under the sudden tension, separating the train with an explosive bang that sounded like a gunshot, and triggering emergency brake applications that ground the entire run to a halt. This physical limit completely reframes the story of the big blow. Its ultimate struggle was not a failure of internal locomotive engineering. The massive turbine performed exactly as designed, generating a level of tractive effort that left conventional diesels far behind. Instead, the issue was systemic. The machine had become too powerful for the very infrastructure it was built to pull. Raw horsepower and torque become entirely useless when the physical connection between the power source and the cargo cannot survive the journey. The train itself was the weak link in the chain, serving as a harsh lesson in systems design. A machine is only as capable as the weakest component in the entire network. To understand how this massive locomotive interacted with its trains, we must look at the fundamental distinction between horsepower and tractive effort. Horsepower is a rate of doing work over time. It requires speed to exist. At a dead stop, a locomotive produces 0 horsepower at the rail, no matter how hard its engine is roaring, because the train is not moving. Tractive effort, however, is the actual physical force of friction and torque applied to the rails. Unlike horsepower, tractive effort is at its absolute maximum at 0 speed. When the big blow stood at the head of a freight train, its starting tractive effort was rated at over 212,000 pounds. This starting force was the dangerous moment. At 0 speed, the locomotive had the physical ability to deliver a massive spike of torque directly to the first metal link behind it. If that force was applied too quickly, the result was a phenomenon called shock loading. In a standard 100-car freight train, the slack between the cars acts like a giant steel spring. Every coupler has a small amount of free play. When a locomotive starts moving, it must pull the slack out of each car one by one. If an engineer opened the throttle too fast, the front of the train surged forward while the rear was still stationary. By the time the force reached the middle or end of the train, the sudden tension hit a single coupler with the force of a massive hammer blow. The drawbar on the lead cargo cars became the weakest link in this long chain of steel. Operating the big blow required far more than simply pulling a lever and letting 8,500 horsepower do the rest. Spec sheet bragging rights meant nothing without precise technique in the cab. To prevent the train from tearing itself apart, Union Pacific engineers had to learn a highly disciplined throttle ramping procedure. On steep mountain grades like the Wasatch Pass, an engineer could not simply throw the controller into full power. Instead, they had to feed the electricity into the traction motors slowly and methodically, ramping the control input at a rate of no more than 10% per second. This gradual application allowed the traction motors to gently build torque, slowly stretching the couplers and absorbing the slack throughout the entire length of the train. The engineer had to feel the train stretch, listening for the sequential clatter of couplers tightening down the line. If the engineer timed it correctly, the massive machine eased its heavy train into motion without a single violent jerk. But if they hesitated, or if their hand moved too quickly on the throttle, the sudden torque spike found the weakest knuckle in the consist and snapped it with the sound of a gunshot. The ultimate success of this giant machine rested entirely on the skill and patience of the person in the engineer's seat. In 1955, the economic logic of the gas turbine was simple and mathematically sound. Union Pacific could justify the turbine's high fuel consumption because it burned bunker C, a heavy, tar-like residual oil left at the bottom of the refining barrel. Sold as a cheap waste product, bunker C cost just 60 cents a gallon, compared to 68 cents for refined diesel. This price gap allowed the big blow to outpull traditional locomotives while keeping operating costs competitive. The machine's financial viability rested entirely on the assumption that this residual sludge would always remain cheap because nobody else wanted it. But the refining industry was quietly changing. During the late 1950s and early 1960s, petroleum refiners adopted fluid catalytic cracking, using zeolite-based catalysts to extract higher-value products from the heaviest parts of the crude oil. Instead of leaving large quantities of thick residual oil behind, refineries learned to crack these heavy molecular chains into gasoline, lighter distillates, and chemical feedstocks for the rapidly growing plastics industry. Almost overnight, what had been treated as useless industrial waste became a valuable raw material. As a result, the share of crude oil ending up as residual fuel fell from 27% to 23%. The supply of cheap bunker C shrank, and its price began to climb. By 1963, the cost of residual oil had risen to 77 cents a gallon, while diesel fuel sat at 81 cents. That original 4-cent price gap had narrowed to almost nothing. To keep the turbines running without destroying their internal blades with heavy sulfur and ash, Union Pacific was forced to buy a cleaner, more refined grade of heavy fuel oil, which cost virtually the same as diesel. The market had shifted underneath the locomotive. The big blow was still a mechanical marvel, but its primary economic advantage had vanished, leaving its financial future incredibly fragile. At full load, the big blow's turbine was expectedly thirsty, but the true economic failure occurred when the locomotive was doing absolutely nothing. Unlike a piston-driven diesel engine that can throttle down to a low RPM idle, a gas turbine must maintain incredibly high internal operating speeds just to keep from stalling. To sustain combustion and keep the high-speed axial compressor spinning without a flameout, the turbine had to run near its thermal limit, even when generating no electricity. Because of this mechanical reality, the turbine was incapable of idling efficiently. According to General Electric's turbine performance charts, when the big blow stood completely still with zero electrical load, its turbine still consumed roughly 90% of its full power fuel flow. The machine burned through nearly 200 gallons of heavy fuel every single hour it sat idling. By comparison, a standard diesel-electric locomotive of the era, like an EMD-SD40, consumed just 30 gallons of fuel per hour at rest. This single engineering trait transformed yards, terminals, and passing sidings into financial black holes. In daily operations, freight trains frequently encounter red signals, bottlenecked yards, and dispatch delays. For a diesel-powered train, waiting on a siding was a minor operational expense. For the big blow, every minute spent motionless was a punishing financial penalty. Shutting down the turbine to save fuel during a temporary delay was rarely practical, as restarting the massive engine required waiting through the 15-minute fuel preheating cycle all over again. This unforgiving cost behavior dictated where and how the big blow could run. The locomotive was completely unsuited for local freight, yard switching, or routes with frequent stops. To remain even marginally viable, the fleet had to be kept in constant high-speed motion on long, uninterrupted mainline runs across the open country of Wyoming and Utah. The big blow was built to conquer mountain grades through raw power, but the cost of motionlessness made it a liability the moment the wheels stopped rolling. The massive power of the big blow required an equally specialized support network that existed nowhere else on the rails. This was not a plug-and-play locomotive that could be patched up with standard tools or serviced at any ordinary division point. Keeping this complex fleet running depended entirely on a custom-designed, hyper-localized maintenance ecosystem concentrated at Union Pacific's Ogden Maintenance Facility in Utah. Ogden served as the sole sanctuary for these machines. The facility was equipped with 3 dedicated turbine test stands, built specifically for high-temperature hot section inspections. It housed a highly specialized parts inventory stocked with custom turbine blades, high-temperature seals, and preheater assemblies, delicate components completely alien to standard diesel shops. To work on these advanced power plants, Union Pacific had to run a specialized training program where mechanics completed a rigorous 200-hour turbine maintenance course. Only 12 certified mechanics per shift were qualified to perform these delicate procedures. This extreme concentration of expertise created a fragile, brittle system. Because the parts and specialized knowledge were locked in a single geographic location, the locomotives were tethered to a narrow operational corridor. If a turbine suffered a mechanical issue far from Utah, the railroad faced a logistical nightmare just to transport the dead locomotive back to the one facility that could fix it. When an essential component failed that Ogden could not fabricate on-site, the entire machine was paralyzed. Replacement parts, such as custom-wound generators or turbine rotors, had to be ordered directly from the General Electric plant in Schenectady, New York. A single faulty blade or warped high-temperature seal could sideline an entire train set for weeks while awaiting a custom shipment from across the country. The Big Blow was a mechanical titan, but it was utterly captive to this fragile, one-off support world. Union Pacific had built a powerhouse, but its survival hung on a single corridor, a handful of trained hands, and a specialized shop in Utah. The ultimate victor on the rails was not another single-unit giant, but a system of smaller, modular machines. Diesel-electric locomotives, like the Electromotive Division's GP30 or SD40, did not try to be extraordinary on their own. Individually, a 3,000 horsepower diesel was vastly weaker than the Big Blow, but it possessed a quiet, devastating advantage: operational flexibility. These standard diesel units could be coupled together in whatever numbers a specific train demanded. If a run over the mountains required 9,000 horsepower, dispatchers simply coupled 3 units together. Once the train cleared the summit and reached flat ground, the extra units could be uncoupled and reassigned to other duties or shut down to save fuel. If one diesel in a set suffered a mechanical failure, the remaining units could still pull the train to its destination, preventing a total line blockage. Standard diesels were also completely free from the geographical tethers that paralyzed the turbines. They required no specialized preheating equipment or custom fuel delivery systems. They could run on any track, pull any type of freight, and most importantly, be serviced at any ordinary maintenance shop across the country. A mechanic in Nebraska or Iowa could swap a piston or repair a generator using standard tools and off-the-shelf parts without needing a dedicated training course or custom shipments from New York factories. Ultimately, the Big Blow did not lose to a more powerful engine. It lost to a superior system design. The steady rise of modularity proved that a network of interchangeable, flexible components is far more valuable than a single point of concentrated brilliance. In the complex world of modern transportation, compatibility and adaptability almost always outrank raw power. On December 26, 1969, the final gas turbine electric locomotive run on Union Pacific rails came to a quiet end. By 1970, the railroad formally retired the entire fleet, bringing a swift conclusion to an era of unmatched single-unit power. Only a few years after these machines dominated the mountain passes of the West, the turbine concept evaporated from American railroading. The dismantling of these titans began almost immediately. Throughout 1971 and 1972, the physical remnants of the fleet were systematically cut up for scrap. Units 27 and 27B were moved to Houston to be broken down with torches, while other turbine cores were sent to General Electric's shop in North Salt Lake to be stripped of their valuable components. The massive steel structures, which once shook the ground miles away, were melted down. Almost none of these machines survived. Today, only 2 complete units escaped the scrap torch: A Unit number 18 and B Unit number 26, both preserved at the Illinois Railway Museum. The rest of the 30-unit fleet vanished completely, leaving behind only scattered components, like a lone turbine rotor or a salvageable fuel heater, in museum displays. The rapid clearing of the tracks was the final proof that the experiment had ended. The era of the single-unit giant was gone, leaving behind only a quiet silence where the great roar used to be. Modern railroading eventually solved the problem of moving massive tonnage over mountain grades, but not by building a larger, more powerful locomotive. Instead, the industry redesigned how force is applied to the train itself. This solution is distributed power. In a distributed power system, locomotives are no longer concentrated solely at the front of the train. Instead, individual units are placed in the middle and at the very rear of the consist, linked together and synchronized by radio telemetry. This physical separation fundamentally redefines the forces acting on the couplers. When a train starts or climbs a steep grade, the pulling force is shared across multiple points along the entire line of cars. This mechanical shift protects the physical hardware of the train. By pushing from the rear and pulling from the middle, the system limits the maximum tension on any single coupler. The peak draft forces that once sheared cast steel knuckles are divided into smaller, manageable loads. A modern 9,000-ton train can traverse the same mountain passes with a 30% reduction in peak coupler forces compared to a lead-only locomotive configuration. The true conceptual successor to the Big Blow was not a bigger engine, but a smarter network. The industry abandoned the pursuit of concentrated brute force at the head end, choosing instead to balance physical strain throughout the entire system. This transition from concentrated single-unit output to coordinated, distributed power allowed railroads to run longer, heavier trains than ever before, proving that system integration is ultimately more successful than raw power. Today, modern railroads haul unprecedented tonnage, not with single brute force giants, but by distributing power throughout the train. The turbine's legacy forces us to confront a fundamental question. Should designers have foreseen that couplers would inevitably fail under such concentrated force? Or is the only way to discover a system's true limit to build a machine powerful enough to break it? Join the conversation in the comments below.